Hello and welcome. Today I'm going to introduce a material property known as Poisson's ratio, and we can use this parameter to find out the change in length or volume of components, and this Poisson's ratio can have a different value for different materials, and we'll see what the effects of those different values may be. So moving on, if we look at a component, we've got a bar here at length L, and if we think about the direct stress and strain, if we put an axial force onto that bar, then you'll already know that it's going to change its length, so it's going to increase in this case by delta L due to the load, and we know that that strain is the change in length over the original length. Some other things that we know about materials under direct stress, we know that the Young's modulus is stress over strain. So E in this case is our Young's modulus. This is stress, and we know that stress is force over area as well. And we can rearrange this equation so that we could say strain equals stress over the Young's modulus as well. So we can kind of relate our change in length to our stress and the material property Young's modulus. But when we put that load on, what happens to the width, the W value on here? Well, it's probably obvious, but we would expect that to decrease, wouldn't we? And in this case, we've got a decrease, or we've got a strain in that direction. It's W, but we've not applied a stress onto there. So how can that happen? Well, we'll find out on the next slide. For a material that we use most commonly in engineering, like steels and aluminiums, which we would consider as an isotropic material, then if we apply a stress in the x direction, this will be accompanied by a strain in the other two orthogonal directions, in this case the y and the z. So as I mentioned previously, we have a strain in those two directions, but we haven't applied a stress to them. For a material that's within its elastic limit, then the relationship between the longitudinal strain, i.e. the strain that's in the direction of the applied load, and the lateral strain in the two orthogonal directions is known as Poisson's ratio. And the definition for that is here in the bottom in the red box. Then Poisson's ratio is minus the lateral strain over the longitudinal strain. And we can see here this minus is important because if we consider the example here we've got, then the x direction is a positive strain, but in the y and the z directions that will actually get smaller, so that's a negative strain. So we can see here simply then our Poisson's ratio, for instance, is equal to the strain in the minus the strain in the y over the strain in the x, and also minus the strain in the z over the strain in the x. From an engineering point of view, what would be really useful would be to be able to work out what these lateral strains are when there's a longitudinal load placed on a component. So, if we look at our relationship here, our Poisson's ratio is minus the lateral strain over the longitudinal strain. We can rearrange this for our lateral strain, and here we have our longitudinal strain, and remember from one of the previous slides, then that strain can be equated to the stress in that direction over the Young's modulus. So we could now take this relationship and put it into this equation, and that will give us that our lateral strain equals minus Poisson's ratio multiplied by the stress in the longitudinal direction over the Young's modulus. So we now have a formula that gives us that strain in relation to the applied load, because we can always work out what this value is, because it's going to equal F in the X direction over the area of the component. And let's not forget, we can do that also for the Z direction. That will give us a similar relationship, and we can always equate those strains to our change in length over the original length. So if we can, from this equation here that I'm starring, work out what the strain is in the Y, if we know what the overall size is in the Y, we can work out then what the change in the Y direction is. And that can be important for quite a number of things. If we've got maybe a shaft with a collar clamped around it, and we put an axial load on that, so if we put a tensile load on it, the diameter will get less, and that collar that's clamped around it may actually come loose. So it's important that we can calculate out what this relationship will give us effectively. Let's look at an example then. So we've got a bar here, diameter of 20 millimeters, and it has an axial load of 50 kilonewtons. It's made of steel, it's got a Young's modulus of 200 gigapascals, and here we've got a Poisson's ratio, which is typical for steel, of 0.3. So we need to find out what the change in diameter is. So remember that in this case our diameter will relate to the Y and Z directions effectively. Here it'll be the same on both, won't it? And that relates to our Poisson's ratio, which we've got, our Young's modulus, which we've got, and we would need to find out what the stress is in the X direction. But again, we've got all the information to find that out, because we know what the load is, and we also can calculate what the cross-section area is, A. So if we put the numbers in there, we've got a load of 50 kilonewtons, and that's divided by the area of a circle, pi r squared or pi d squared over 4, and that gives us 159 megapascals. So we can take that value now, put that into there, and we should be able to determine what the strain is in the Y and the Z directions. So our Poisson's ratio is 0.3. We've calculated our stress at 159 times by 10 to the 6 pascals, and our Young's modulus is 200 times 10 to the 9. And that gives us a value there of minus 239 times by 10 to the minus 6. So don't forget this minus sign at the beginning, and this minus sign means that the diameter is actually getting smaller. So the final thing we need to do is remember that strain is change in length over original length. So in this case, our change in diameter, so if our strain equals change in diameter over original diameter, then if we rearrange that, we get our change in diameter equals the strain times by the diameter. So our strain that we've just calculated, 239 times by 10 to the minus 6 times by, and this is done in millimeters, times by 20 millimeters, gives us a very small change in diameter, minus 4.77 times 10 to the minus 3 millimeters in terms of the decrease in diameter. So hopefully you kind of followed all the way through that, and we'll move on to the next slide. Okay, so we've got an example here. We've got a block of material, this blue block, and onto there, this little yellow thing that we can see on here is a strain gauge. And I think we've probably covered strain gauges in the measurement module, but it's a device that will change its electrical resistivity depending on the amount of compression or tension that's applied to it. So it gives us a readout that will measure the strain of a particular component. So if we put a load in the x direction on here, so we put a stress onto this component, then if we look at the graph on the left hand side, then as we put the load on, we would see that we would get some strain in the x direction. If at time t1 we've got on here, so at 1 second here, we apply a load in the y direction, what do you think will happen to the strain in the x direction? Well, let's put it on and have a look. So if we put a load on in the y direction, then because of the nature of the material, because of Poisson's ratio, if we put a load on in the y, it will give a strain in the longitude, in the lateral directions. So therefore it will decrease the strain in the x direction due to that. So this kind of illustrates that we have to be really careful when we think about measuring the stresses and strains on components, because the effects of putting a stress on in different directions, or 2 or 3 stresses on a component, can greatly affect the measurements that we take. Okay, if we take our little component again and we put a load on in the x direction, so we get a stress in the x direction, we will get a corresponding strain in that direction as well, so we get this strain in the x direction. If we put a load on in the y direction, then we'll get a load in the y direction. But thinking about the effects of Poisson's ratio, if we put a load in one direction, we get a corresponding strain in another, and each one of those is related with this equation here at the bottom. So for each one of those directions, then we can include that into the equation for the strain in that particular direction. So let's look at the x direction. Then we've got the strain due to the load in the x direction minus any strain caused by a load in the y direction as well. So we can now quantify this amount of dip that we saw here, this on the previous slide, where when we put the load on in the y direction, we would expect to get a decrease in the strain in the x direction. Well, the amount of decrease there we can now calculate, which will be this, which will be Poisson's ratio multiplied by the stress in the y divided by Young's modulus. And if we take that into 3 dimensions, so if we put a stress in the z direction as well, then we can just include that into each equation as well. So you can see there's commonality between all of these three equations here. For each one, we've got our direct stress-strain kind of relationship. So this is coming from E equals stress over strain. And on each one of these, we also have these additional terms added to the equation now. So we take off the strain caused by any stresses in the other directions. So let's have a look at an example then to see how that affects our kind of calculations. Sorry, just before we get to the example, we need to think about the volumetric strain. So each of the strains in the x, y, and z directions, if we add those together, we'll get a total change in volume of this component. And just as we do with strain in the x, y, or z directions, where strain is change in length over original length, we can do the same thing for volume. So our volumetric strain is change in volume over the original volume. So if we can see, if we can work out what each one of these stresses are in the x, y, and z, we can work out our volumetric strain. And then if we know the original volume, which presumably we do, we can then work out what the change in volume will be. So if we had this component, we could work out how much its volume is going to change, and that will be directly related to the stresses in the x, y, and z directions. Here's an example then to work out what the change in volume is of this particular bar. So it's a 10mm square bar and 1mm long. So we could easily work out the original volume, and we know that it's got an axial load of a kilonewton. It's made of steel. That shouldn't be a minus on there. That should be equals 200 gigapascals. And again, it's got a Poisson's ratio of 0.3. So as we had in the previous example, we can work out what the strain is in the x direction. So our strain is stress over the Young's modulus, and here we have our stress, which is force over area. And if we put those values in, we can work out what the strain is in the x direction. For the, and I suppose I just need to mention that I guess on this diagram that's the x direction, and we'll have a y direction and a z direction. So in the y and the z directions, then we have our Poisson's ratio multiplied by the stress in the x over the Young's modulus. And we can see there we've already worked out what this value is effectively here. So you'll notice that that value there is just the strain in the x direction. So we've worked that out at 50 times 10 to the 6. So we put that in, multiply it by minus 0.3, gives us the strain in the y and the z directions. So all we need to do, if we add those three up, we can work out the change in the volumetric strain, and then we should be able to work out what the change in volume is. So the volumetric strain is our strain in the x direction minus the strain in the y minus the strain in the z. So that gives us 20 times 10 to the minus 6. And then finally, our change in volume is our volumetric strain times by the original volume. So here's our strain, and our original volume, it's 1000 millimeters long, and its cross section is 10 millimeters by 10 millimeters. So if you bung the numbers in there, then you get a value of 2 cubic millimeters increase in volume. We know now then that our volumetric strain is just the summation of the strain in the x, y and z directions. And we also have the relationship for the strain in those directions related to the different stresses that could be on it. So in the three-dimensional scenario, we'll have a strain in the x, y and z directions. So if we think about that, we've got a component here that's subjected to stresses in the x, y and z directions. Then for each of these strains, if we expand effectively the strain x, y and z, then for the x, for instance, then the x strain will be that bit, and the y strain will be that part, and the z strain will be that part. So you can see in each third of this equation, effectively, it's in that standard format. So for the x direction, we've got the strain in the x direction, so that comes from our stress over Young's modulus, and then that's minus the Poisson's ratio multiplied by the strains in the corresponding y and z directions. And if you kind of collect the terms together, then we get this relationship here at the bottom. So it's a fairly encompassing equation. It means that we don't have to calculate out all of these separate terms in order to find our volumetric strain as we did in the previous example. We can just find, as long as we know what the stress is in the x, y and z directions, and we know the material properties, then we can work out the overall strain, and then obviously we can then calculate what any change in volume might be. So let's have a look at using that equation then. In this example then, we have the same component as we had on the previous example, a 10 millimeter square bar. It's a meter long, but in this case now we have an additional 5 kilonewton load in one of the lateral directions, so we'll probably call that y direction. So remember the equation that I've just introduced, which is this one here, and if we can calculate out what our X stress is and our Y stress, then we'll be able to work out what our strain is and also what our change in volume is. And we know that this one, sigma Z, is going to equal 0 in these equations. In the X direction then, our X stress is 1,000 newtons over the cross-sectional area, which is 10 millimeters squared. So I've done this in newtons per millimeter squared. Moving on, we can look in the Y direction. So we have a much larger load, 5 times the load, but we also have a much larger area in the Y direction. So it's a meter long, so it's 1,000 millimeters multiplied by 10. So that gives us half a newton per millimeter squared stress in the Y direction. So these two values now we can just put into the top equation. So we've got 1 minus 2 times by Poisson's ratio over the Young's modulus, multiplied by the summation of the different stresses. So in here we've got, this one is sigma X, obviously, and this is sigma Y, and the 0 is sigma Z. If we calculate that through, then we get a volumetric strain of 21 times 10 to the minus 6. And then we can finally calculate the change in volume. We know that's the strain multiplied by the original volume. So if we put the corresponding numbers in there, then we can see that we get a increase in volume of 2.1 millimeters cubed. So in the previous example, where it just had the 1 kilonewton load on, we had an increase of 2 millimeters. So you might first think, well, putting a 5 kilonewton load on in one of the other directions would make a huge difference. But hopefully you'll see the reason it hasn't made such a big difference is, although it's 5 kilonewtons, it's applied over a much bigger area here. So if we kind of try and highlight that, it's applied over a much bigger area, so it actually doesn't really create a large additional stress in the component. We have a list here of some typical values for different materials, and if we look at some of the ones that we use quite commonly, then we've got things like aluminium, which 0.32, steel 0.27 to 0.3. So if you look at most of the materials on here, we've kind of got values between, I don't know, 0.2 to 0.4 maybe. We've got some interesting examples at the top and the bottom of the table. We've got rubber, which has got the highest Poisson's ratio of 0.5. And very interestingly here, we have cork at the bottom. And it's interesting because it has a value virtually of 0. And that means then, if we try and put a cork into a bottle, so we put a force on our cork to seal the bottle, to seal our wine in it, it means when we put that force on there, we will obviously get some change in length of our bottle, of our cork. So I don't know whether I can highlight that on here, whether you can see this or not. So if I draw a little red box, we would expect our cork there, it would shorten a small amount, so that could be delta X. But what we would expect with cork then is that this strain in the Y direction is going to be 0 because its Poisson's ratio is 0. So it means that we can quite easily get cork into a bottle. If we tried to do the same thing with rubber, however, you'd never get it in the bottle, because when you push down on the rubber cork, then it would squash out half as much again as you've squashed it down, so you'd never be able to get it in the bottle. So I just thought that was quite an interesting little fact, that the ancient Greeks and Romans kind of were utilizing the 0 Poisson's ratio of cork way before we ever started thinking of it from an engineering point of view. Okay, that's it for this lecture. The next one we will start to look at how Poisson's ratio affects pressured cylinders. So we look at pressure vessels, things like gas canisters, even things like a can of Coke. How does the volume of those cylinders change when we put an internal pressure on them. Okay, thanks for listening. Goodbye.